You climb into the attic on a July afternoon, and the heat hits you like a physical wall. The air is thick, smelling of old pine studs and dry insulation, and if you touch the underside of your roof boards, they are hot enough to fry an egg. Most homeowners look at that blazing roof and see a problem to be solved by buying a $2,000 solar array or running a noisy attic fan that draws 70 watts from the grid just to push hot air around. We have been taught that power is something you must always buy from somewhere else, delivered through a thick black wire, metered and billed to you every 30 days until you die. Stop and think about that. We spend thousands of dollars to insulate our ceilings to keep that massive heat from pushing down into our living rooms, while the roof itself is acting as a giant passive collector, gathering more energy in a single afternoon than the appliances below it consume in a week. I saw the alternative to this cycle with my own eyes in Holmes County, Ohio, inside a small, quiet workshop that hasn't been connected to a utility pole since the timber was framed. There were no glass panels glinting on the roof, no massive banks of lithium batteries humming in the corner, and no high-voltage warning signs. Yet the overhead LED shop lights were bright, a small tool charger was active, and a 12-volt fan was moving a steady, cool breeze across the workbench. The source was a simple galvanized metal box, no larger than a standard boot carton, bolted directly to the ridge of the barn. It had no moving parts, it made no sound, and it cost less to assemble than the price of 2 large pizzas. Understand this clearly. I am not promising you a miracle device that will run your central air conditioner or power a welding rig. It will not do that. If someone on the internet tells you that you can run a whole modern suburban household off a handful of scrap metal and a temperature gap, they are selling you a fairy tale. The laws of nature are strict, and they do not yield to wishful thinking. This method has an honest limit. It produces modest, steady power, between 15 and 40 watts during peak daylight hours, tapering down to a tiny trickle at night. But 40 watts, flowing quietly and reliably without a fuel tank or a monthly statement, is enough to handle the baseline essentials that keep a small homestead or a workshop functioning. This is not a new discovery, nor is it fringe science. In 1923, a Lancaster County blacksmith named Eli Stoltzfus built the first documented version of this harvester using scrap tin, copper wire, and a salvaged magnet from a crank telephone exchange. That box ran a bank of small bulbs in his shop for over 40 years without a single repair. The underlying principles belong to the bedrock of classical physics. It relies first on the Seebeck effect, discovered in 1821, which proves that when you join 2 different metals and expose one side to heat and the other to cold, electrons begin to push through the circuit, creating a continuous electrical voltage. It then pairs that with Faraday's principle of induction from 1831, capturing the tiny, natural pressure differentials that cause air to move along the peak of a building. The federal government understood the value of this decentralized approach long before the modern energy grid became a centralized monopoly. If you look into the archives of the United States Department of Agriculture, specifically Farmer's Bulletin, number 1448, published in 1925, you will find this exact device listed under the dry title of an auxiliary roof-mounted thermoelectric harvester. It was actively promoted to isolated American farmers as a way to achieve basic energy self-sufficiency using local materials. Yet, by the early 1950s, those bulletins were quietly removed from active circulation, and the practical knowledge vanished from the public consciousness, preserved only within plain communities that refused grid connection by religious conviction. Why did we forget? The answer is simple. There is no corporate profit in a device that costs $20, lasts for 40 years, and cannot be metered. Centralized utilities needed captive customers to justify the massive capital required to string copper lines across the continent in the mid-20th century. As one early rural electrification administrator noted in his private correspondence, The goal was to make the farmer as dependent on central station power as the city dweller, because that was the only path to economic modernization. We didn't stop using these devices because they failed. We stopped using them because we were persuaded to forget how to make our own power. When you break the system down, it is elegant in its simplicity. On a typical summer afternoon, the south slope of a dark metal or asphalt roof can easily reach 150 degrees Fahrenheit under direct sunlight. Meanwhile, the shaded north slope or the deep crawl space beneath the house remains closer to 85 degrees. That 65-degree gap is a massive, untapped reservoir of potential energy bleeding into the sky every single day. By using small, modern thermoelectric modules, which cost about $4 each online, and are essentially the reverse of the cooling chips found in portable car coolers, we can sandwich that temperature difference between a small collector plate on the hot roof and a simple finned aluminum heat sink inside the cooler attic air. The heat flows through the ceramic module, trying to find a balance, and as it does, it generates a steady stream of direct current. It is a strange sensation the first time you assemble one of these arrays. You carry a flat piece of metal out into the yard, connect two simple wires to a common multimeter, and lay it down on the hot grass. You watch the needle jump or the digital display register 3, 5, or 8 volts out of nowhere with completely silent passivity. There are no gears turning, no chemicals degrading, and no solar cells to crack. It feels like watching water flow uphill, but it is simply the natural result of heat moving toward cold through a conductive path. But understanding the theory is only the first step. To actually capture that energy safely, to wire the modules so they don't overheat, to build the tiny wind induction element that keeps the current trickling even after the sun goes down, and to mount the box securely so it withstands a winter storm requires specific, careful steps. You have to know how to prepare the metal faces, how to apply the thermal paste so the heat transfers cleanly, and how to route the low-voltage lines down into your workspace without losing half your power to resistance in the wire. To build this harvester, you do not need the precision of a laboratory, but you do need patience and a clean surface. Clear off your workbench, sweep away the soft, and lay down a piece of soft canvas or cardboard. We are working with delicate ceramic squares and soft metals, and a single stray metal shaving on your table can crack a module under pressure. Gather your materials first. You will need 8 standard TEC1 12706 thermoelectric modules. When you hold them in your hand, they feel light like small white, unbaked clay tiles, perfectly square with 2 thin wires, one red, one black, sprouting from one edge. You will also need 2 sheets of copper or heavy-gauge aluminum, roughly 12 inches square. If you can find old copper roof flashing at a salvage yard, use that. It has a dull, brown patina from years of weather, but underneath that crust is a metal that moves heat twice as fast as aluminum. The third critical element is a tube of thermal coupling paste. It is a thick, stark white grease that smells faintly of zinc, soft as lard between your fingers, and its only job is to fill the microscopic valleys in the metal so heat pass through without hitting pockets of trapped air. We begin with the preparation of the metal plates. Take your copper sheets and a piece of fine 80-grit sandpaper. You must scrub the metal until the dull brown gives way to a bright salmon pink shine. Stop and think about this step. If you leave a film of oxidation, oil, or old dirt on the plate, you are essentially putting a blanket over the heat. It must be clean enough to reflect light. Once sanded, wipe the plates down with a splash of rubbing alcohol until the rag comes away clean. Now, lay out your modules. Lay one plate flat on the bench. This will be your hot plate, the side that touches the underside of your roof. Before you apply any paste, you must determine which side of the white Nusreich square is the hot side and which is the cold. If you connect them backward, the current will flow in reverse. Or worse, the modules will fight each other and produce nothing. A simple test will tell you. Hold the module by its edges and touch the two bare wire ends to the terminals of a common 9-volt battery for just 2 seconds. One side will immediately begin to feel warm against your fingertip, while the other goes cold. Mark the hot side with a small pencil dot. Take your tube of white thermal paste. Squeeze a small dollop, no larger than a pea, onto the center of the marked hot side of each module. Use an old plastic card to spread it across the white surface until you have a layer so thin it is almost translucent, like a morning frost on glass. A common mistake here is thinking more is better. If you glob the paste on thick like butter on bread, it acts as an insulator instead of a conductor, and your voltage will drop to near zero. Plie the 8 modules onto your cleaned copper plate in 2 neat rows of 4, spaced about ½ inch apart, with all the pencil dots facing down against the metal. Press each one down firmly, giving it a tiny twisting motion until you feel the suction grip. The white paste will ooze slightly from the edges. That is exactly what you want to see. Now comes the wiring, and this is where you must be methodical. We are going to wire these 8 modules in a series parallel circuit to balance our voltage and current. Take the red wire of the first module and twist it together with the black wire of the second module. Continue down the row, red to black, red to black. This series connection builds up the voltage, stepping it up from a fraction of a volt to a usable level. When you finish the first row of 4, you will have 1 free black wire at the start and 1 free red wire at the end. Do the exact same with the second row. Finally, connect the 2 free red wires together and the 2 free black wires together. This parallel connection doubles the current, ensuring that even on a hazy day, there is enough pushing force to overcome the resistance of the line running down into your shop. Solder these joints carefully and wrap each one in black electrical tape. Next, we must apply the cold plate, the second copper sheet that will face the cool interior of your attic. Apply the same paper-thin layer of white paste to the top, clean faces of the modules. Gently lower the second copper plate onto the array. To hold this sandwich together, you must use nylon bolts or insulated clamps around the perimeter. Do not use plain steel screws through the center of the plates. Understand this: steel conducts heat well, and if you bolt the hot plate directly to the cold plate with a steel screw, the heat will short-circuit through the bolt instead of passing through the ceramic modules. The plates must remain thermally isolated from each other, separated only by the white squares. Turn the entire assembly over so the cold plate faces up. To this plate, you must attach your heat sink. An old aluminum finned radiator from a discarded computer or stereo amplifier works perfectly. It looks like a block of metal with dozens of thin, upright fingers. Coat the base of this heat sink with paste and clamp it firmly to the center of the cold plate. These fins will catch the cooler, moving attic air, pulling the heat away from the back of the modules and keeping the temperature gap as wide as possible. Before you take this assembly to the roof, you must build the housing, the protective box that keeps the weather out. Frame a small box out of simple pine boards, just deep enough to accommodate the thickness of your metal sandwich and the heat sink. The bottom of the box remains open to the attic air, but the top, sun-facing side must be sealed. Cut a piece of single-strength window glass to fit the frame. Paint the interior of the wood frame with a can of flat black stove paint. It has a heavy mineral smell as it dries, and its matte texture is designed to absorb every stray ray of light rather than reflecting it away. Mount your copper sandwich inside this frame so that the hot plate is flush with the top edge, and seal around its borders with a bead of high-temperature silicone sealant. It smells strongly of vinegar as it cures, turning into a tough, rubbery barrier that prevents rainwater from seeping down into the electrical connections. Once the silicone is dry, lay your glass pane over the top and secure it with a few small wooden strips. You now hold in your hands a completed thermoelectric harvester. It is heavy, solid, and completely silent. If you look through the glass, you see only a black, unblinking surface designed to trap the sun. If you look at the bottom, the aluminum fins are ready to breathe the cool air of the structure below. But before you climb the ladder to bolt this box to your ridgeline, there is the second system to consider: the induction coil that turns the passing wind into a nighttime trickle charge, and the method for joining these two distinct currents into a single steady stream that your batteries can accept without boiling. To truly master this craft, you must understand the invisible current you are steering. Nature does not operate on magic. It operates on gradients, on the natural desire of things to move from where they are crowded to where they have room. Think of electricity not as some mysterious, artificial fluid, but like water flowing through a channel on your property. Water only moves if there is a hill, a difference in height between the spring and the pond. If your land is perfectly flat, the water sits still, becomes stagnant, and does no work. The thermoelectric modules we just built operate on the exact same principle, but instead of a height difference, they rely on a temperature difference. Inside those tiny white ceramic squares are dozens of small pillars of two different semiconductor materials, usually bismuth and tellurium. One type of pillar has an excess of Moby electrons. The other has a shortage. When the hot copper plate absorbs the blazing afternoon sun, it agitates the electrons on that side of the module, making them energetic and crowded. The cold plate, cooled by the shaded air of your attic, keeps the electrons on the opposite side calm and spaced out. Stop and think about what happens next. The crowded, energetic electrons on the hot side naturally want to flee from the agitation. They push through the pillars toward the quiet, cool side. This movement, this massive migration of microscopic charges driven by nothing more than a difference in temperature, is what we call an electrical current. The wider the gap between the hot roof and the cool attic, the harder those electrons push, and the higher the voltage your multimeter will register. This brings us to the second force we are harnessing: the natural breathing of the building. As the air inside your attic warms up, it expands and rises, escaping through the ridge vents at the very peak of your roof. At the same time, outside wind rolls up the slope of the building, creating a zone of low pressure right at the ridge. This creates a tiny, localized draft that blows through the ridge vent day and night. By placing a small, lightweight magnetic vane in that path, we aren't building a massive windmill to fight the storms. We are simply catching a ride on the house's natural exhalation. As the tiny neodymium magnet spins past our coil of fine copper wire, its magnetic field cuts through the metal atoms, physically pushing the electrons along the wire. It is basic electromagnetic induction. But let us be entirely honest about the boundaries of this method. I am a practitioner, not a salesman, and this device has strict limits that you must accept before you spend a single Saturday building it. First, let us talk about the materials of your roof. This system requires a high thermal conductivity to function efficiently. If your home is covered in thick, traditional cedar shakes or heavy concrete tiles, this harvester will perform poorly. Wood and concrete are natural insulators. They hold heat stubbornly and release it slowly, preventing the sharp, intense temperature spike on the outer plate that the Seebeck effect requires. The ideal surface is a dark metal roof, steel or aluminum, painted flat black or dark green. Metal reacts instantly to the sun, driving the temperature of the hot plate up to 160 degrees within minutes of a cloud passing. Standard asphalt shingles will work, but their output is roughly 30% lower than metal because the asphalt layers absorb a portion of the energy before it reaches your copper collector. Second, understand the atmospheric limits. This device is entirely dependent on the climate and the season. In the peak of July, throughout the American Midwest, the South, or the high deserts of the West, the harvester is a reliable worker. The sun is high, the roofs are scorching, and the attic spaces stay relatively cool compared to the roof deck. But come January, the rules change. If you live in a northern latitude, say northern Maine or the Canadian Plains, and your roof is buried under 6 inches of snow, the thermoelectric portion of the device will drop to 0. The snow acts as a perfect blanket, keeping the roof at a uniform 32 degrees on both sides. There is no gradient, no hill for the electrons to run down, and therefore no power. During those winter months, you will rely entirely on the induction coil catching the sharp cold winter winds rolling over the ridge. Third, you must recognize the scale of what you are collecting. This is a trickle harvester, not a powerhouse. A single shoebox-sized unit will never run a microwave, a toaster, or a washing machine. Those appliances require thousands of watts instantaneously. If you attempt to wire this device directly to a heavy load, the voltage will instantly collapse to 0, and you risk overheating the modules from the inside out. This system is designed exclusively to charge a small battery bank over time. It is a slow, steady accumulation, like gathering rainwater in a barrel drop by drop. If you let it collect for 10 hours, it will easily provide enough stored energy to run low-voltage LED lights all night, charge your communication radios, and keep a small 12-volt circulation fan spinning. If you need more power, the only path is scale. You cannot make a single module work harder than the laws of physics allow. You can only add more modules and more boxes along the ridge, just as the bishop did behind his barn. Understand this final limitation. The electronics are the fragile link. The copper plates will outlive you, and the magnets will hold their strength for a century. But the small charge controller that manages the current is vulnerable to moisture and lightning. If you do not seal the box perfectly, the damp, humid air of a late summer attic will slowly corrode the circuit board. It must be housed in a weatherproof junction box, inspected yearly, and treated with the same respect you give any other utility connection on your property. Now that you know exactly what this device can and cannot do, we are ready to look at how these two different forms of power, the steady heat-driven DC voltage and the pulsing wind-driven AC current, are brought together into a single control panel without destroying each other. When you hold a finished harvester box in your hands, you are not holding a piece of modern alternative technology. You are holding a thread that connects you to an era when self-reliance was not a hobby, but a foundational American value. The story of distributed roof-mounted energy did not begin in a Silicon Valley laboratory, and it did not start with the environmental movements of the late 20th century. It began in the dusty workshops of practical men who looked at the landscape and hated waste. In the early decades of the 1900s, before the giant steel towers of the central utilities marched across the fields, the federal government actively encouraged farmers to generate their own power. The United States Department of Agriculture understood that an independent farmstead was a resilient farmstead. In 1925, they released Farmer's Bulletin number 1448. If you look at the faded, sepia-toned pages of that document, which you can still find if you dig deep enough into the basement archives of the National Agricultural Library in Maryland, you will see clear, hand-drawn schematics for what the bureaucratic authors called an auxiliary roof-mounted thermoelectric and induction harvester for isolated farmsteads. The bulletin was not an academic theory. It was a practical field manual distributed to tens of thousands of rural families. It explained how to use the intense heat trapped under tin roofs to generate a steady current for charging the early glass jar radio batteries and running basic telegraph or lighting lines. In the 1930s, scientists at the Smithsonian Institution took these concepts even further. Dr. Charles Greeley Abbott, who served as the 5th Secretary of the Smithsonian from 1928 until 1944, spent years building and measuring distributed solar thermal harvesters. In 1936, he published a seminal paper through the Smithsonian's Astrophysical Observatory, proving that an ordinary home could harvest up to 60% of its domestic thermal and electrical needs using simple, passive roof-mounted collectors. Yet, if you look at the annual reports of the Rural Electrification Administration from 1937 through 1946, you can trace the exact moment the tide turned. A massive coalition was formed between expanding utility holding companies and federal planners. The goal shifted from helping farmers make their own power to building a captive, centralized customer base that would pay a monthly bill forever. Bulletin 1448 was quietly pulled from active printing cycles in 1946 and never reissued. The knowledge didn't fail. It was systematically archived to clear the path for the modern utility grid. But old knowledge is stubborn. It survives in the corners where the modern world is ignored. The plain communities of Ohio and Pennsylvania never forgot these principles because they never signed the contracts to connect to the central station wires. For over a century, their blacksmiths and carpenters have passed down the oral blueprints of the ridge catcher, refining it with whatever materials were at hand. From old telephone magnets in the 20s to salvaged copper flashing today, modern science continues to quietly validate what these craftsmen have known for generations. In 2009, the Oak Ridge National Laboratory released Field Report ORNL-TM209215, which monitored passive thermoelectric arrays over an extended period. Their conclusion was striking. The solid-state modules showed zero meaningful degradation over a 25-year service life, making them one of the most durable, low-maintenance energy harvesting systems ever tested by the state. Stop and think about that. The data is sitting in public archives. The physics has been settled since the days of Faraday and Seebeck. The materials are sitting in your local hardware store or scrapyard right now. The only thing missing from this equation is your willingness to remember what we were taught to forget. This weekend, before the season turns and the roof becomes slippery, I invite you to take the first step. You do not have to build a massive system on your first afternoon. Go out to your shed or your garage on a sunny afternoon with a simple digital thermometer. Touch it to the south slope of your roof, then take a reading on the north slope or inside the crawl space. Look at that gap, that 30, 50, or 70-degree temperature hill. Realize that this difference in heat is a pressure valve bleeding energy into the sky every single day your house stands under the sun. Building one of these boxes is not a complex engineering feat. It is an act of simple carpentry and basic wiring. It requires no specialized credentials, no permits from a utility company, and no thousands of dollars in debt. It requires an investment of about $20, 4 hours of focused work at your bench, and a willingness to trust your own hands. There is a deep, quiet satisfaction that comes on the afternoon you mount your finished box to the ridge. Run the thin, low-voltage wire down through the attic hatch and watch a bank of workspace lights flicker to life for the first time. You realize that the wires running from the pole on the street are not a lifeline. They are simply a convenience that you can choose to rely on less and less. The roof above your head